Good morning, friends. It's my pleasure to be here for again my course Flight Mechanics. I am in the module 4, which is maneuvering performance. I have already completed 3 lectures on that. Turn performance, then pull up, pull down. These all things I have already covered. Today I am going to cover about VN diagram or flight maneuvering envelope. This we will be observing here. I am Dr. Yagya Dutta Dwivedi, professor from Institute of Aeronautical Engineering, Department of Aeronautical Engineering, Hyderabad, India. Today my topics overviews are flight envelope, charts in conducting their flight operations, VN diagram, load factor, maneuvering diagram, VG diagram. This diagram I will be covering. So first I will discuss about Man Ki Baat, means what I want to say about maneuvering. As of now, we have seen that load factor is N and this is L by W. So as we increase the load factor, the aerodynamic forces are increasing. Your wing and other things start bending upward. If it is the positive load factor, it will bend upward. So how much lift? So if N is equal to 2, it means 2 times of the weight. That much it is pulling upward. So if you see the fighter aircraft, they have 9, 10, 11, 12. So that type of hard, your wings are required, your all body of the aircrafts. So your structural parameter, your aerodynamic parameter, your thrust, very high thrust required for the countering this type of load factors. So in this we have some aerodynamics constraint, we have the structural constraint. So if your aircraft is flying with V star of corner velocity and less than that time your aerodynamics constraints V stall will come into play. But if it is flying more than that, then structural parameters will come into the play. This is also, if you are climbing or pulling up, that time the pilot which is flying or the passengers, they will feel lot of trouble. And if a human can sustain only up to load factor 6, as the load factor is increasing more than the 6, if you are going up for the pull up, your blood will come down, and if you are coming down, your blood will go up. So your brain may be starving, or your brain may have excess blood, which may cause the unconsciousness of the human. To prevent that, every pilot of the fighter, they will wear the G suit, that is called anti-G suit. This suit will allow that your body will not immediately be affected by the pull-up or the pull-down maneuvers, and your blood pressure will be maintained within the limit. That is the objective of this G suit. So I will go for my next topic, which is flight envelope. Flight regime includes all permissible combination of speed, altitude, weight, and the center of gravity. This regime is shaped by aerodynamics, propulsion, structure, and dynamics of the aircraft. The border of these flight regimes are referred to as the flight envelope or the maneuvering envelope. So these are the conditions, that is aerodynamics, propulsion, structure, and the dynamics. These envelopes are shaped in that way, and these all borders are giving the same thing. The safety of the passenger are guaranteed by the designers and manufacturers in these boundaries. Pilots are trained to fly within this envelope. Since the aircraft will not be stable, controllable, structurally not strong if fly outside of this limit. So if we fly out of this envelope, which is called the flight envelope, there may be some stability problem, controllability problem, structural damage, and some other things may happen. A mishap or a crash is expected if flown outside of this limit. So we have to fly our aircraft within the flight envelope. Otherwise, the aerodynamic problem, propulsive problem, structural or other problems, stability and other things will come into play. So now charts in conducting their flight operations. So we have some different charts. Here I am explaining about 4 types of charts which pilots should know. And as an engineer, we should also know, because for designing this thing, we are the people who are designing the aircraft. And in this designing process, we should understand what is the Mach number and what is the coefficient of lift which we are getting on the aircraft. So the first chart we should know is diagram of variation of aircraft lift coefficient versus Mach number, that is CLM. Diagram of variation of airspeed versus altitude, VH. Diagram of variation of center of gravity versus aircraft weight, that is XCG versus weight. Diagram of variation of load factor N versus V, VN diagram. So for our case, we will be very much focusing on the 4th point, that is variation of load factor N versus speed V. So it is called V capital and small n, VN diagram. So we will be discussing about this VN diagram. This envelope demonstrates the variation of the allowable load factor, that is N, versus airspeed V. In other words, it depicts the aircraft limit load factor as a function of airspeed. So limit load factor, N limit versus velocity of the aircraft. Allowable load factor is function of strength of the aircraft, and producible load factor is a function of the engine thrust. We have discussed this, that if it is allowable load factor is a function of the strength of the aircraft material, wings and other things. But if we talk about the producible load factor, it's depend upon the engine thrust or power. And we have seen T by W. Okay, so this is very important. And in the next slide, I am going to discuss about VN diagram, which is very, very important for our study. So for the VN diagram, we are plotting the load factor in x-axis. This is the load factor. Load factor, it is denoted by small n, and the speed V is in this direction. If you see here, the 0 is here, and it is the minus negative load factor, and this side is positive load factor, and this side is negative load factor N. N negative and N positive. If you see here, from here, if you draw the line up to certain limit here, this is the V stall, this is the speed of the stalling speed in the positive stall area. This is the positive stall area, and this is the negative stall area here. This is the negative stall area. And this area is your corner velocity V star. This I have discussed in my previous class, that this is the corner velocity. Here is the maximum dynamic pressure This zone is maximum Q or dynamic pressure. This is the structural zone, this and this. Structural failure due to the, and it is the due to the high velocity. This is the V and E, never speed velocity. So this I have explained here. This is the safe zone. I will just draw the green line, so it will be nice that if you are flying in this zone, very safe. If you fly in this, not very safe, but you can fly. Very best is this area. If you fly in this, it is a very nice. So this is A, it is a corner velocity, and this is very important because from here, if you exceed, your structure will damage. If you decrease, stall will happen. So you have to fly in this zone, not in this or not in this. This is the stall speed here. This is the V star corner speed, VC and the VT. So now we will discuss about this, all the things. Load factor. There are several forces that are acting during a flight operation, such as aircraft weight, engine thrust, lift and the drag. The weight of an aircraft on the ground air is naturally produced by the gravity. There are other sources of load on aircraft during flight, as inertia force, that is centrifugal force, and the gust load. In some instances of flight, such as turn and the pull-up, the aircraft must generate a lift force such that it is more than the aircraft weight. So this load factor is equal to AC by G plus 1. So here load factor, it is a load factor is equal to L by W. Now I will discuss another diagram, that is called the maneuver diagram. The VN diagram is basically an envelope that indicates the limit of the load factors and speed for a safe flight. So in this VN diagram, we can find out the limits of the load factor and the speed, safe speed of the aircraft. The load factor is the maximum allowable N, not the maximum producible N. So here load factor, we have to see the maximum allowable by the structure, but not the producible by engine. This diagram is sometimes referred to as the maneuvering diagram. It is usually composed of 3 lines plus 2 curves. Sometimes we see call this maneuvering diagram. It is composed of 3 lines plus 2 curves. The 2 curves on the left hand side represents the aerodynamic limit on the load factor imposed by the stall, that is the CL maximum. The 2 straight lines on the top and the bottom represents the maximum positive and the negative allowable load factor. The central vertical line on the right represents the maximum allowable airspeed. Point A is then called the maneuvering point. At this point, both lift coefficient and the load factors are simultaneously at their highest possible value. So this point A is very important because here CL is maximum and load factor is also maximum. So here same diagram. So this is the maneuvering point. Maneuvering point, here CL maximum is high and N maximum is also there. So this point is, we have to take very much cautious of this. The corner velocity which we have seen in this diagram, this is the V star, that is the corner velocity. The corner velocity is an interesting velocity for fighter pilots and acrobatic aircraft. At a speed less than V star, it is not possible to structurally damage the aircraft due to the generation of load factor less than Nmax. So if you are flying less than this, your aircraft will not be damaged. At a speed greater than V star, maneuverability decreases. Since the speed is too high, this point simultaneously corresponds to the tightest turn and fastest turn of an aircraft. The general aviation aircraft like Cessna 172 has a maneuvering speed of 97 knots, while its stall speed is 47 knots. Typical corner velocity of the current advanced fighter are around 250 to 304 knots EAS, equivalent airspeed. Here we can see that two flight maneuvers with a high load factor: A. Lockheed Martin F-16CM fighting Falcon in an inverted flight, and B. Dassault Rafale in a very high bank angle. So it has got 90-degree bank angle. It can get, but this has the advantage in that it can go inverted flight for a long time. So these are the two maneuvering shown in this diagram. Now I will go for the detail of this diagram. Here we can see the VS. So if you see here, VS is for 1G is 200 knots at 30,000 feet. So this is the VS here. VS is 200 knots at 30,000 feet. It is a stall speed. Stall speed of the aircraft. This is the line. VS increases with altitude due to the density reduction. As you go high altitude, your VS will be also increasing. Beyond 740 knots, if you see here, beyond 740 knots, this is the 740 knots, above 6.5 G, 6.5 G, and below minus 2.5 G, minus 2.5 here, 2.5, here is a 2.5 G, structural airframe damage will happen. So if you are here below, above 6.5 G and below this, structural damage, this red line, red zone, structural damage will happen. So stay well within this limit. So your aircraft should be within this limit, and if you see the here altitude, as you go higher and higher and higher altitude, stall lines will also change. So stay well within this limit. V and E, never exceed speed. This is here, I think. So never exceed speeds. Beyond that, structural damage may take place. If you are going your speed more than the V and E, your VD, here it is shown VD, your aircraft may go structurally damaged. So significance of the military VN diagram. So previously we have seen the commercially or other aircraft, but now here military aircraft. So this you can see 0 to 12. Most of the time, if you see, this is the 7.5 military aircraft. This is the positive limit, and here minus 3 is the negative limit. This is your speed limit. Area of the structural damage or the failure limit due to the air speed 575 knots. Structural failure, positive ultimate. This is the ultimate. Structural damage area from here to here, it is permissible. In an extreme case, damage may not happen. This is the envelope where your aircraft can fly. This is your flight zone. This is the zone your aircraft can fly. This aircraft up to 11.25 damage may not happen. This A is a maneuver velocity. Your aircraft, if you fly in this, maximum maneuver you can obtain. So these are the few significance which I have discussed. Structural damage area, a negative ultimate. This is the line. Structural damage area, 100% damage will happen if you are here in this zone, in this zone. So this is the depiction of some military aircraft. It is called military because here we have 11.25 load factors are present. In the normal aircraft, it may be 3 to 5 positive and minus 2 to this negative. So factors affecting airplane strength: gross weight, the W of the aircraft; aircraft configuration, the fuel tank, missiles, loading and extra; summary, symmetry of the loading due to turn, due to the climb, bank, extra, your symmetry will be disturbed; applicable altitude. So rho also is matters. In the next class, I am going to discuss these topics: revision of drag polar, minimum drag velocity when alpha t is equal to 0, relation of CL and CD naught for maximum CL, maximum CL, minimum drag speed, power required to maintain steady level flight. These are the references: Anderson, JD, Aircraft Performance and Design in International Edition, McGraw-Hill's first edition; SL by ME, Aircraft Performance Theory and the Practice, AIA Education Series, AIA. Any questions you can ask to my this email, ydwedi@gmail.com. Please do like and subscribe my this channel. Please put the comment if you are feeling that anywhere some problem is there, you are not understanding. I will try to explain your issues. Till then, goodbye. See you. Thank you very much for the joining my class. Be tuned for my next lecture.
Like, share and subscribe. Hit the bell icon for more updates.